Hi everyone, my name is Andrey. I'm a researcher at the University of Manchester, and this is the second video on flexibility of active distribution networks. In the previous video, we considered why some networks can be called flexible, why flexibility is a popular research topic, and why it is that important for distribution system operators. We then focused on models for estimating the boundary of the flexibility area. In the literature, these areas are usually called P-Q flexibility areas or nodal operating envelopes. Today we move forward and we will analyze not only the limits of the aggregated flexibility, but also the optimal flexible unit dispatch. For example, we will try to minimize the cost of flexibility service provision. We will analyze control actions and some coordination issues of flexible units, and we will see that actually the flexible unit dispatch is very complex. It is affected by many parameters, such as cost functions, and by many network constraints. The results that I'm about to show today are mainly reported in these two manuscripts. I worked in Julia, JUMP, Julia for mathematical programming, and I mainly used Gurobi solver. So again, if you're interested in details, please check these manuscripts. I will put links in the description. Now let's go to the case study. The main case that I use in my studies is the IEEE 33-bus radial distribution network. It is a very popular case study which can be visualized like this. This is quite an unusual visualization. I used GapFi software for network analysis to create this graph, and let's discuss a few things about this picture. So first of all, you might notice that each bus is shown by a circle, and the size of these circles is proportional to the nodal demand, the electrical load at these buses. So we can easily understand where the demand is located in this network. This network is radial, as we can see. There are no loops, and it has only 4 feeders. The next thing that you can notice is that we use different colors to highlight the nodes, ranging from green to orange and red. These colors are used to show the voltage levels at each bus. For example, voltages at buses close to the primary substation, also called TSO-DSO interface in this study, those voltages are close to the nominal value of 1 per unit, and they are highlighted in green. But the further we move away from the primary substation, we have more and more voltage losses, and we see that voltages become quite low in this network. If you consider bus 18, it is highlighted in dark orange color because its voltage is about 0.91, which is quite low. And actually, as we will see, this will be quite a significant constraint for the operation of flexible units in this network, because voltage is already quite low at some substations. So quite an interesting figure. It shows the topology of the network, it shows where the demand is located, and it also visualizes the voltages. Now, how can we analyze the flexibility of this network? Well, we decided to place 4 flexible units in this network, 1 at the end of each feeder. As you may see, we denote these units as FU, so there is FU22, FU25, 33, and 18. For simplicity, we will be calling these units not by their bus number, but as letters A, B, C, D. To make this analysis more interesting, we placed 4 identical flexible units in this network. By identical, I mean that they have equal P-Q regulation capabilities. If we plot their capabilities here, we will see that they're indeed equal and they have these box shapes. So each unit can regulate flexible power by plus minus 500 kilowatts and plus minus 500 kilovolt ampere reactive. Now, the only thing that is different about these units is their cost functions. So again, as you can see in this picture, we assign different costs for flexible power regulations for these units. Flexible unit D, located at bus 18, is assumed to have the cheapest flexible power. And you can see here that its flexibility cost function is $300 per megawatt hour. Then we have more expensive unit C, $325 per megawatt hour, unit B, $350, and the most expensive unit A, $375 per megawatt hour. So we have quite an interesting setting for this case study. We have 4 flexible units. They have identical capacities, identical P-Q capabilities, but different cost functions. And we will see in a moment how this works when we will try to minimize the cost of the system operation, and we will try to find the optimal flexible unit dispatch. Now, we discussed that these units have identical P-Q capabilities, but we are not interested in the individual flexibility of each unit at some particular substations. We are interested in the aggregated flexibility of this network. Therefore, we need to find the limits of this flexibility at the primary substation, in this case at substation number 1. So we can activate different units, or all of them together, and see what is the boundary of aggregated flexibility area at this substation number 1. Let's see how it looks like. So if we analyze the aggregated flexibility at the primary substation only from flexible unit 22, unit A, we will see that this area resembles actually a box. It is a bit changed, a bit stretched and deformed, but still resembles the original P-Q capability chart. If we analyze the flexibility at the primary substation from unit 25, we will see a similar picture, but this time a bit more stretched and deformed. This happens because of the nonlinearities of the optimal power flow model. Since we have voltage losses, power losses, we see that the shape of the original box is changing. But if we consider the flexibility that we can get from unit 33, we will see that this shape is completely different from the original box. We will see that it is much more stretched and deformed, and moreover, it is reduced from the top right corner. This happens because of some network constraints and some voltage issues. So we see that aggregated flexibility from this unit cannot be fully utilized. We cannot increase much P and Q consumption of this particular unit because we will face voltage issues and we cannot get any more flexibility from this unit. Then, if we activate unit 25 and 33, we will get an aggregated flexibility area like this. Recall that unit 25 didn't have any voltage issues. Only unit 33 had them. But when acting together, when jointly providing flexibility, we get this new area which combines constraints from both units. So if one of the units has some constraints, this is reflected in their joint aggregated flexibility. By activating different flexibility units, we can see actually how the aggregated flexibility is formed and what constraints are there. Then, if we activate all units together, we can estimate the absolute limits of aggregated flexibility, and we can produce a picture like this. So again, we see that this network is quite flexible. We can deviate from the initial operating point, we can increase power consumption or decrease it, and this is what most of the papers do when they analyze the aggregated network flexibility, where they estimate nodal operating envelopes. We discussed this in the previous video, how we can do this using iterative optimal power flow models, where we can approximate the boundary solving point-by-point OPF problem. So yeah, for this case, we did the same. We found the boundary of the aggregated flexibility area. But what happens inside this boundary? How to operate flexible units at each feasible operating point? This question is not really explored in the literature. And from now on, I don't want to show you just the results and these figures. I want to kind of tell you a story of how we discovered this behavior. So we wanted to understand how to operate flexible units within this P-Q flexibility area. Well, to understand this, we need to solve the optimal power flow problem for some operating points. But for what points and for how many points? If we select randomly 100 points, 100 feasible points within the boundary, we can get a picture like this. And yeah, you will see that we have a grid of solutions, but first of all, is this enough to analyze that many solutions? To me, discretizing this space with just 100 points seems not accurate enough. There is too much space between different solutions, and it's not really clear how to analyze them. It became clear to us that to properly analyze flexible unit dispatch, we need much more points to analyze. And in my research, I computed optimal power flow problem about 25,000 times. So I discretized this feasible PQ space with 25,000 points. This was the first step, but the next question is, okay, I solved the cost minimizing OPF problem 25,000 times, but how even to display, to present these results and analyze them? Because we have 4 flexible units and we have different dispatch of them, 25,000 different results, and it was not even clear how to present this. So the first solution that we found is to present 4 subfigures, each figure for each unit, and each figure should be showing the percentage, the share of the flexibility provided. Let's take a look at this visualization. So you can see 4 subfigures, flexible unit A, B, C, and D. The color map of this figure corresponds to the allocation of the flexible power between the units in percent. So the dark blue color shows that some units are allocated up to 100% of the requested flexibility from the network. And the light blue color shows that some units are producing no flexibility, so they have 0% of their share in this flexibility request. So once we produced these results, once we created this visualization, we were very happy because at first glance, these results make sense. If you see, for example, what happens with flexible unit D, let me remind you that this is the cheapest flexible unit, we see that it produces a lot of flexible power for the low magnitude flexibility requests. I mean, requests that are close to the initial operating point. And yeah, this flexible unit produces up to 100% for such low magnitude flexibility requests, which makes sense. Then if we check what happens with more expensive units like unit C, we can notice that it is not producing any flexible power close to the initial operating point. Again, this is perfectly logical. This unit is more expensive, so why should we activate it to provide some flexibility here? And then if we consider even more expensive units like unit B and A, they are not activated at all for such low magnitude flexibility requests. They are producing some flexible power only when we move closer to the boundary of the flexibility area. There is no way to reach the absolute limits of the aggregated flexibility without activating all 4 flexible units. Therefore, we should use flexible power even from expensive units like flexible unit A. So from the economic standpoint, these results make sense. We activate cheapest unit first, unit D and C, and then more expensive units B and A. First, we were very happy about these simulations because they show economic principles of flexibility markets. But then once we spent more time analyzing the results, we actually understood that something is wrong here. We even thought maybe we made a mistake in the simulations, because just check how complex the results are. Why there are so many nonlinear changes happening in the allocation of the flexible power? Why is the optimal flexible unit dispatch so complex? Why do we see so many nonlinear changes and shifts in the flexibility provision? It almost resembles some chaotic figures. I know that there should be no chaos in this system. The constraints are just quadratic, they are not complex enough. But still, why are these images so complex? Let's try to understand what is happening in these pictures. So as I said, unit D, the cheapest unit, is producing a lot of flexible power in the beginning for low magnitude flexibility requests, but then suddenly its share of flexible power drops. And especially we can see that it drops a lot once we start moving towards the direction of active and reactive power consumption increase. So if we're moving to this upper right corner of this figure. So it is clear that something affects the optimal flexible unit dispatch, probably network constraints and voltage issues. But still, why are these results so complex? Why do we have these strange shifts between the flexible power allocation between the units? We were thinking about these results for quite some time, and then it became obvious to us that in order to analyze and explain this nonlinearity of the flexible unit dispatch, we need to display many more parameters. We need to know not only the shares of flexible power allocated to each flexible unit, but we also need to know exact flexibility regulations by the units. We need to know which units produce active power P, which units consume active power P, and which units perform regulations for reactive power or some voltage control, and so on and so forth. So this figure that I show you has 4 subfigures, but if we introduce more parameters like P and Q regulations, consumption and production, this means many more parameters. How can we even display that? I'm very happy that we found a solution to show this, and it looks like this. So I know that this is quite a complex figure, and we will stop here for some time to discuss the details. And what you see here is basically 2 sets of figures. So the upper 4 figures, they are called flexible active power management in megawatts. So we see here how units regulate their P, their active power consumption. We see that the figures have some colors, white, blue, and red. And in this case, the color map corresponds to the consumption and production. Consumption is shown in red color, production is shown in blue color. And if unit is doing nothing, it is not activated, not producing, not consuming any power, these areas are shown in white color. Then at the bottom, we have the next set of subfigures showing flexible reactive power regulation, reactive power management, so Q regulations in megavolt ampere reactive. And the same logic applies here. We show in red if units are consuming reactive power, in blue if units are producing reactive power, and in white color if units are doing nothing. And keep in mind that this map is showing the solutions for 25,000 optimal power flow problems, where we tried to minimize the cost of the flexible unit dispatch. So just appreciate how complex it is. And here actually we see why the behavior of flexibility provision is that complex and nonlinear. We see some rapid changes in the flexibility provision, and I would like to discuss this with you. Let's try to analyze what is making sense in this figure. So first thing that is making sense here is that if we consider the initial operating point shown by this cross marker, every unit is doing nothing. So we can see that these areas are shown in white color, and again, this makes sense. So if we do not need to produce any aggregated flexibility, we do not activate flexible units. Then, if we want to increase consumption of the network, let's say we want to increase active power consumption P, so we are moving to the right direction, we start activating units and they start consuming more flexible power. And we can see that these parts of the map of this flexibility area are highlighted in red color. The same thing happens if we want to decrease the aggregated power consumption of the network. We move to the left and we see that flexible units start producing flexible power, so they start generating flexibility, therefore reducing the overall power consumption of the network. Recall that units have different cost functions. Unit D, for example, is the cheapest one. So once we move to a certain direction, let's say again to the left, reducing active power consumption of the network, this unit, unit D, is activated first. And then unit C joins, and then unit B. So this makes sense. But the complexity comes from the operating points where we try to increase the overall power consumption of the network. Why? Because when we do this, we need to overcome some network constraints, including the voltage issues that I mentioned earlier when we considered the topology of the network. For example, the cheapest unit, unit D, is located at bus 18, which has quite a low voltage in the initial operating point. If we want to further increase power consumption of unit D, we cannot do this a lot because we will face voltage constraints soon. And if we continue doing so, the operation of this network will be infeasible. Since unit D cannot increase its consumption much, other flexible units start helping him with this flexibility request. And you may see that unit C, for example, also starts consuming active flexible power. And then unit B joins, and so on and so forth. But this time, when we increase network consumption, the behavior of the units is very complex and nonlinear. And what do I mean by this? If you consider a path from the initial operating point to any operating point with the increased power consumption, you will see that along this path, we will be crossing some different operating regions. In some regions, the unit consumes power, then stops consuming power, and then consumes it again. So quite a strange and nonlinear behavior. And even the shapes that we see in this figure, they are not like linear or quadratic, ellipsoidal. We see very strange shapes, sometimes triangular, sometimes just rapid changes. And actually, we can even find here some islands. For example, let's check the reactive power management by flexible unit C at bus 33. We can see that there is a point where there is an isolated area where this unit should be consuming power. And if we are operating in this area, it is optimal for this unit to consume flexible reactive power. Once we move a little bit from this area, the unit should be doing nothing. So the unit is not activated. And again, these solutions are very strange and very complex and very nonlinear. How can we operate a system like that? I hope you enjoyed these beautiful pictures of flexibility regulations by different units. And we spent a lot of time analyzing different operating points. And then we found very strange solutions. We found solutions where flexible units were simultaneously producing and consuming flexible power. And this doesn't make sense because we want to find the optimal flexible unit dispatch. So we want to minimize the cost of flexibility regulations. Why should we consider regimes where some units produce power and consume power? So this is like double cost of this regulation. And then we realized that this happens not because of the economic model, not because we want to minimize the cost of flexibility regulations. This happens because of the nature of flexible power provision, because some units have to perform this active network management and increase or decrease their flexible power consumption in order to overcome certain network constraints. And this active network management that we called power swaps in our paper is quite controversial because actually it puts the operation of distribution network at risk. Imagine what will happen if one unit is producing flexibility while others are consuming flexible power. And this one unit that is producing power is doing this just to keep the operation of the network feasible, for example, to control low voltages at some substations. If this single unit fails, all other units will fail and the operation of the system will fail and there will be voltage collapse or something else. And let me show you this. Let me show you what I mean. Let's check the figure again. Let's consider reactive power management and let's check what is happening with the operation of the units. So imagine that we want to increase the overall power consumption of the network. So we are moving to the right and we want to activate the units according to our cost minimization model. So we should first activate unit D and make it consuming a reactive power. So there should be some red area, but we don't see it in this picture. If you check, we are moving to the right from the initial operating point and unit D is doing nothing. It is not consuming reactive power, even though it should be doing this. So clearly it is not consuming reactive power because of the voltage constraints. The voltage is already too low at this substation. But not only this unit doesn't provide any reactive power management, once we move to the right even further, flexible unit D starts producing reactive flexible power, which doesn't make sense because we are asking the system to consume more flexible power. And the same happens with flexible unit C. If we check what is happening with the regulations, this unit is not activated, and then once we move to the right, it starts producing reactive flexible power. So clearly these two units are performing power management just to control the voltages and keep the operation of the network feasible. But wait, if the aggregated network flexibility corresponds to the regime of the increased flexible power consumption, so who is consuming flexible power? Because these two units are producing it. And the answer is that expensive flexible units A and B are consuming flexible power. So clearly there is some power swap happening in operating points to keep the operation of the network feasible. And as I said, the operation in such points could be quite dangerous for the system. So the next step that we did in our studies, we tried to forbid this active network management, and we tried to forbid these flexible power swaps. In order to do this, we created additional constraints. We said that each unit in the system can only produce P or consume P. And the same happens with Q, reactive power. And when we introduced these no power swap constraints, we got flexibility area boundaries reduced, and they look like this. So you can see the new boundary with no power swaps shown here by dashed line. This boundary is much smaller, and moreover, it is nonlinear and non-convex. The area is non-convex. We can clearly see this if we show a picture like this. So this is the new boundary and the initial boundary where power swap was allowed. And this is an interesting finding of our study, that if we assume perfect network coordination, we get these P-Q flexibility areas, which sometimes look convex. But once we have some coordination issues, or if we assume that this power swap is not possible or not reliable, the aggregated P-Q flexibility areas shrink a lot and they become non-convex. And this poses additional challenges to the operation of distribution networks. So by analyzing 25,000 feasible operating points, by analyzing this optimal flexible unit dispatch, and not only the dispatch but also the active power regulations, reactive power management, we were able to identify these interesting issues of flexible power regulation. For example, we found that there are some risky areas where flexible units perform the power swap. We also found this strange nonlinear behavior of flexible units, which actually can pose challenges to the operation of distribution systems. For example, because some units will have to perform their flexibility regulations rapidly. During the revision of one of our publications, one reviewer asked an interesting question. How can we measure the nonlinearity of this flexible unit dispatch, and what are the problems related to these nonlinearities? I think this is a very interesting and exciting topic, so I want to talk a bit more about the nonlinearities that happen in the flexibility provision. And before going to the nonlinearities of the flexible unit dispatch, let's just talk in general about nonlinear functions. Why are they problematic, and why are they bad in some sense? They are problematic because sometimes nonlinear functions can change faster than linear functions, and sometimes unpredictably, if we do not know exactly what are the nonlinear functions that we are dealing with. To illustrate this, I created a simple example for you. I generated an S-curve, a sigmoid function, and let's see how the nonlinearity of this function can be measured. So consider a nonlinear sigmoid function like this. It is growing slowly at the beginning, then we have a sharp increase, and then it is not growing again. We can compare this function with the linear function shown here by dashed line, which is growing steadily from 0 to 1 all the time. So clearly, the nonlinear function, the sigmoid function, has some rapid changes, especially compared to the linear function, which can cause some problems if we do not know where exactly these changes will happen. So let's try to measure this nonlinearity. How can we do this? How can we measure this fast growth of the function? Well, there are many techniques to analyze nonlinearity of the function, but one technique is to break the function into intervals and analyze changes within the intervals. First, to illustrate this method, let's divide the space into, let's say, 10 intervals. And then, within each interval, let's measure by how much this nonlinear function changes its values. So we can compute the maximum change in the values of this function, and we also know the interval that we used to measure the nonlinearity. Then we can compute the nonlinearity factor, which is the ratio between the maximum change in the value of the functions to the size of this step to the width of this interval. And in this manner, we can measure the nonlinearity of a function for each interval that we created. In this picture, we consider 10 intervals, but we can consider, let's say, 50 intervals to measure the nonlinearity of the function more accurately, or even 200 intervals, and we can get a picture like this. So what we see here, shown by this red heat map, is actually the areas with the highest nonlinearity of this function. And we can say that those are the dangerous areas, because if we do not expect this rapid growth of the function, this could cause some problems to the system. This was a simple example of measuring nonlinearity of a sigmoid function, where we found a space of some rapid shifts, and we can say that those areas are dangerous for the operation. But how can we measure the nonlinearity of the estimated P-Q flexibility areas? You remember we computed 25,000 points, so to measure the nonlinearity and to find some rapid shifts in the flexible unit dispatch, we need to analyze those points. And the question is how to do this. And the answer that we propose in our papers is similar to this sigmoid function analysis. We propose to break the flexibility area in the feasible intervals and to compare maximum changes in the flexible unit dispatch. And this algorithm can be visualized like that. So what you see here is a simple grid with 12 points, and the values at the vertices of this grid show some flexible power of a unit. Let's say we don't care about active power, reactive power. Let's say this is just some power regulation by the unit. And then we should estimate the absolute norm corresponding to the maximum changes between these points. So for each of these areas, for each region, we can estimate the maximum shift in the flexibility regulation. For example, let's consider the first region here, located at the bottom left of the figure, where we have 4 operating points with flexible power 0, 1, 1, and 1. What is the maximum change between these flexibility regulations? It is 1, because 1 minus 0 is 1. And if we assume that the distance between these points in the P-Q space is also 1 unit, this means that nonlinearity factor for this area is also 1. So no fast, rapid changes are happening here in this area. But there are some other regions in this figure, for example, the region located in the center with the operating points corresponding to flexible power provision 1, 2, 3, and 2. So the absolute norm of the maximum change in this region is 3 minus 1, 2. So we can say that in this area we have some nonlinear changes in the flexible unit dispatch, because the distance between the operating points is 1 unit, but the flexible power regulation changed by 2 units. And we have even worse case located in the top right corner of this figure, where we have flexible power capacity of the unit 1, 0, 3, and 3. And the maximum change is 3. So something really fast and nonlinear happens in this region. This is a simple example of the nonlinearity assessment algorithm that we proposed in our paper, with the idea that we need to analyze operating points nearby to estimate the nonlinearity and to find any nonlinear rapid changes in the flexible unit dispatch. Interestingly, this algorithm is similar to the edge detection methods that are used in computer vision and image processing. In such methods, there is a kernel function that corresponds to the pixels in the image, and by defining this kernel, we can manipulate the image. For example, we can find edges of the objects in this image. And we are doing a similar thing in our nonlinearity assessment algorithm. We are trying to detect the edges of the areas, regions, where there exist some rapid nonlinear shifts in the optimal flexible unit dispatch. And remember, we have 25,000 feasible operating points, so we need to compare these points with each other, and we produce the figure like this. And I think that this figure shows the real beauty and the real challenge of flexible distribution networks. I mean, just look how complex it is. Remember that the original P-Q capabilities of the units were given by these box shapes. And some network constraints, they are quadratic functions, which should be looking like ellipsoidal constraints. But here we see nothing like that. There are no boxes and no ellipsoids in these pictures. Instead, we see much more strange and complex shapes here. We see some triangles, some edges that resemble waves, and yeah, it is really hard to explain why the shapes look like that. The only thing that we can say for sure is that this map can guide distribution system operators how to navigate in this aggregated flexibility area and how to avoid regions with rapid nonlinear shifts in the flexible unit dispatch. So if we consider some regulations corresponding to the decreased network power consumption, for example, if we move to the left from the initial operating point, we see that there are no edges, no rapid shifts detected by the nonlinearity assessment algorithm. We can say that this is a safe area and network operators can easily control the units to get there. But if we want to increase the aggregated consumption of the network and we move to the right or up in this figure, we can get to these dangerous areas with rapid nonlinear shifts. And I mean, just look at these nonlinearity factors. In some areas, in some of these regions, we see nonlinearity factors of 16, which means that if we produce 1 more kilowatt of flexible power, some units can be forced to change their flexible power by 16 times more, by 16 kilowatts. I believe this is a very interesting finding, and it can change the way distribution networks will be operated in the future because of these distributed renewable energy resources. How are we going to control these flexible resources? We should control them not only precisely, but also some of these flexible units should be able to perform regulations very rapidly, as identified by this nonlinearity analysis. There will be some areas that distribution system operators might want to completely avoid, not even to create these sophisticated control strategies and avoid any issues with power swaps and rapid nonlinear changes, and so on and so forth. I hope that you enjoyed the models and simulations that we considered today, and I hope they help you to better understand how actually the flexibility of active distribution networks work. Some takeaways from today's simulations. First, that it is not enough to analyze the limits of the aggregated flexibility, not enough to analyze this boundary. It is also necessary to understand how actually the flexible units will operate within this flexible area. And we saw that the optimal flexible unit dispatch can be very tricky and complex. There could be many issues with units coordination. We need this active network management. We need power swaps. Some units have to perform very rapid flexibility regulations, which obviously will pose challenges to the distribution system operators. And yeah, I think there is much more research needed here to analyze the nonlinearity of flexibility provision. There are a few more aspects about aggregated network flexibility that I would like to discuss with you, such as pricing of flexible power, flexibility markets, some game theoretic models, and other features like network reconfiguration. I plan to make a few more videos about each of these aspects. I hope you enjoyed today's discussion and perhaps learned something new. I will see you soon in the next videos on the aggregated network flexibility. Have a nice day. Bye.